And then we have a basis set. What do we need in a basis set when we expand something on a basis set?
Oh,
Projections.
We need projections, all right?
so is the Fourier integral of the probability density, which is the projection of the summation of waves in wave space?
It's getting there. That's very close, man. Yeah. All right. Very good. All right. So the words are probably harder to do than to write it out. So let's write it out a bit, okay? Everybody ready? So here we go. Let's look for our 1D well for advice. Our 1D well, our infinite 1D well. What did we find? We found out that our solutions were that psi, I'll make it the total, psi n of x and t equal e to the minus I e n over h bar t, and then radical 2 over, when is that right? Yeah, 2 over a sine k n x. All right? Everybody okay? And then what we did is these were our stationary state solutions. And then what we got is our total general solution. Our general solution of x and t equals summation over n of Cn of psi n of xt, where these are our stationary state solutions. Okay? So, again, the words that I want you to see here is what type of summation is this? This is a discrete summation, but it's over infinite, so denumerably infinite. This represents something what I would call a Fourier series. All right? Now, a couple other terms that I want to introduce. So, because it's going to carry over to what we're doing today. So let's say we have the infinite well, we have minus a plus a. All right, and we have something like that. We have this solution right there. All right, that's one of the stationary states. Right, it's psi 2, right? That's psi 2 of x without the time dependence. Okay. So this right here is x. This space. So this is what I would call an x space representation. Right? It's my x space. It's what my wave function looks like according to x. Okay, when I look at this, I'm transforming it to what space?
Function space.
Well, I'm transforming it to a function space, but it's a function space of what new variable?
Okay.
K. Alright, this is like a k-space representation. So I'm going to call this one k-space representation.
Fourier analysis.
That's why I wanted to mention this. This is Fourier again, Fourier series. You guys, some of you guys did this in experimental already, but this is a Fourier series representation. So over here, I could simply write it like this. I could write my Cn's versus my Kn's. Right? And if I'm just talking about just one of these stationary states, that n equals 2 stationary state, then what does my k-space representation of this wave function look like?
Just a single vertical line.
A single vertical line where?
K2.
That's right.
Can you repeat that?
Right there. And the height of this would be C2. I don't know about that. But this would be at K2. Okay, so let's back up. So some of you guys like Fourier analysis in terms of frequencies and sound, which is a time. So look, you have a time-dependent signal, like say a sound wave, like you're singing a C note. Everybody sing a C note so we can get this right. Okay, Jeremy probably has it, but I can't tell, all right? So you have a C note, right? It's a function of time. When you do the Fourier series transform of a C note, it goes from time-space, time representation, to what?
Frequency space.
Okay, so check it out. It's time over here to 1 over time over here, right? And so how many peaks will I have in my frequency space representation of a pure C note?
Just one.
Just one. Okay? I'm doing the same thing here, but am I doing something as a function of I messed up a little bit with the time thing, but it's a function of x, right? Because these are stationary. When you calculate the expectation values of stationary states, what happens to the time dependence? Yeah, it goes away, all right? So this is essentially x space representation. So before I had time space, and when I did a Fourier series, I went to 1 over time. So if I have x space, I'm going to do the Fourier series. What am I going to? 1 over
X.
1 over x. And here, x is, instead of it, so time, you go from time to 1 over time, but we say the period of the signal, so that's frequency. So then you're going from x, you're going to 1 over x, but instead of using x, you're going to use the wavelength. And then 2 pi over the wavelength is k, the wave number. So you go into the k space or wave number representation. So what I'm saying here is that, and so this is the Fourier series representation. It's the same thing. It's a different representation of the same function. This is what it looks like as a function of x. This is what it looks like in its wave number space. So how many wavelengths go into making this one signal? 1. So how many k's? 2 pi over 1k. So this is like a C note in time. This is like the C frequency. But this is the C wavelength, all right? The C note in x, and then this is the C note wavelength.
So I didn't, that doesn't seem like that. So can you just clarify that one more time?
I don't know what that means.
They don't, you said one of those makes that?
Yes.
Graphically, I guess, it's going to come up.
Okay, so Mike, if I sing a C note, right?
Yeah.
I can plot that pressure wave as a function of time. What does it look like?
Yep.
Sine wave.
Yeah.
All right, what frequency is a C note?
512.
512 hertz. How many other frequencies go into it? None.
None.
So I could either plot that pressure wave as a function of time. That's my time domain representation of a C note, right?
Yeah.
Or I could say it's just equal to one frequency, 512.
And so that other one on the right, that's 512.
Yeah, that's like the 512. But now we're not doing time, we're doing x. So we're going from x to wavelength. We're going you go time to 1 over time, or 1 over period, that's frequency, time to frequency. Here we're going x to 1 over x, and 1 over x is like a wavelength. So
It's basically like before where we had the frequency, and then when you got the frequency space, you just got a spike there. So now if we have that wavelength, we're just going to get a spike at that wavelength.
that wavelength, if I said, oh, that wavelength, it's exactly equal to that wavelength. So
it's just the time representation.
All right.
so
So
you
now,
got it. If you can say that, you got it.
I get it.
And you can't believe, if you guys get that, you can't believe how powerful that is and how far that will take you. The time domain and the space and the frequency, and then the space to wave number.
Can I just mention something that all those frequencies that you'll have on that, if one of them is, you say, identified as a C note, then all of them would be, because if you just divide by half or multiply by 2 a C note, you're still going to get a C note. Because 512 is like 2 or 256 or 128, like they're all C. You know what I'm saying? So I don't know if that's the best analogy to use.
Well,
Yeah.
on
I mean, you
a
would
guitar
have-
But it
string.
makes sense.
You
Like,
don't have harmonics. What's really nice is to combine this into the lab. We do it experimental. You know, it really makes a lot of sense. All right, but look, I don't want to harp too much on this. We've got to solve this problem. All right? We're now going from a Fourier series at the denumerally infinite space to a Fourier integral in infinitely dimension space. All right, so we're now over here into, this is for our 1D well. This is our free particle. And for our free particle, we've got, what did we find? We found that our psi ends of xt, our time-dependent solutions, equal e to the ikx minus bt. Yes, so c1 e to the ikx plus c2 e, oh yeah, it's the fully time dependent. So ikx minus omega t plus c2 e to the minus ikx minus omega t. All right? so what we're going to do is the following. We're going to take the next step, and we're going to say psi general of x and t is going to equal. Now, I have a little bit different notation for Griffiths, but that's okay. And check this out. It's going to be the integral from minus infinity to plus infinity, all right, of psi, little psi of k, e to the I kx minus omega t, and then I'm going to say dk.
You were talking in one of the e's, not both of them?
Okay, so have I really excluded any of the e's?
What he does is you put what k is the...
That's right. What is k? Where does k extend from? We're integrating over k's, so we're integrating over wave numbers. So we're not summing now over wave numbers, we're integrating over wave numbers. And so what values of k can it take?
2 pi over lambda.
No, k's can go from minus infinity to plus infinity. So when k is minus, right, this becomes minus kx. If you take out the minus, it becomes kx plus omega t. And what does kx plus omega t become? The plane traveling wave going that way. And then when k's become positive, yeah, so Alamar's seen it because he's smiling. When you see these things, you smile. All right, this is becoming positive, and then this becomes a plane traveling wave that way. So I have not dropped off either of these. Okay? Very good. Important to notice, these are no longer, remember, we associate Cn squared with the probability that when we measure this general wave function that we get that eigenenergy En. All right, so Cn squared is a probability. All right, what we're going to associate here with is that psi k dk is more like a probability of density. It's a probability, it's related to probability per unit wavelength. Right, because we're now doing the integral over the wavelengths. Okay. Quick note is our Griffiths uses 1 over the square root of 2 pi. All right?
Can I ask one question?
Yeah.
So that would, the psi k squared,
Yeah.
would that equal the probability of finding that wave in its wave state?
Yeah.
Kind of like the C sub n's with the probability of finding the function in that stationary state?
Yeah, so CNs would give you the probability of finding
Squared.
being in that stationary state with energy En.
Right.
So this thing is going to be related to the probability of finding yourself in that, with that traveling wave, with that traveling wave energy.
In wave space representation.
Yes, yeah. All right? Okay. So the next thing is that the hard thing, well, not the hard thing, what we had to do over here is we had to find CNs. All right? And remember, what we did is something like this. We did Fourier's trick, right? And we found out this, is we found that CNs equal the integral of psi of x and t equals 0 times psi n of x t equals 0 dx.
I thought they're complex conjugate.
That's when you're calculating an expectation value. We're not calculating an expectation value here. This is how you do it.
Just the C sub n's?
We're trying to calculate the C sub n's. All right? But psi n of x of t equals 0, it just comes down to this, that Cn equals the integral from minus infinity to plus infinity of psi of x and t equals 0.